Alright, so our first topic here for today, we're going to be looking at, kind of examining the uniqueness of chevalley basis. So, we know that for a fixed base, the hi are determined. But we may vary the x alpha. So we'll say a particular x alpha is replaced by eta alpha times x alpha. Then the bracket of eta alpha x alpha, I guess this is for every element in our chevalley basis. We get eta negative alpha, x negative alpha, oops, that's supposed to be an x. This is of course going to be eta alpha, eta negative alpha, h alpha. So we must have that eta alpha times eta negative alpha is 1 to satisfy our first condition, which they call condition A. Now if A and B are roots with their sum being a root, then the bracket of our scaling factor eta alpha on x alpha with eta beta of x beta is going to be eta alpha, eta beta, of course, of x alpha. I should write this on a new line. So I always do that. I feel like I didn't see how many chained inequalities they have here. So we're scaling up our x alpha by eta alpha. We're scaling up our x beta by eta beta. And so we can bring these scaling factors out to the front. Like that. Then we know that this term on the right is going to be a scaling factor, the structure constant c alpha beta times our, of course we still have our eta alpha, eta beta in there, on x of alpha plus beta, which is equal to, we're going to call it c prime eta alpha beta. We'll just say what that is more specifically later on, times eta of alpha plus beta of x alpha plus beta, and you can just tell what c prime alpha beta is from the fact that this equality needs to hold up, but writing it explicitly, it's c alpha beta is our structure constant times eta alpha times eta beta over eta of alpha plus beta. Now we also, using our inverse in that we constructed before, we also need that this must be equal to c alpha beta of eta alpha plus beta over eta alpha, eta beta. So that the product of eta alpha and eta beta is plus or minus eta of alpha plus beta. And so any function eta from phi to f satisfying the above, namely this equation and this equation, can be used to modify the basis. So essentially we have to get everything in line. We have to scale things in a very particular way, but it can be done in general. Now, we also have to worry about signs, which is a little trickier. We have bracket of x alpha and x beta being plus or minus r plus 1, scaling alpha plus beta, where of course alpha and beta and their sum are all roots. Yeah, but the fact that this is ambiguous is like very much a thing. We can see by choosing, I'm going to call this the matrix with the 1 and 1, 3 and nowhere else. Pick the negative instead of the positive of E13 in a chevalley basis of SL3F. We can have either sign, I think. It says there is an algorithm for making a consistent choice of signs based on just a root system. You can use this to prove the isomorphism theorem, but you need to then, of course, establish that our automorphism sigma is independent of that, otherwise you're just going to be circular. You can also prove the existence of L by writing down the multiplication table and then just working through the Jacobi identity, which is really long and doesn't sound fun. So we're going to go ahead and actually move on to our next section, which is reduction modulo a prime. So the integer span Lz of a chevalley basis of x alpha and hi is a lattice, of course. In L, independent of our choice in base. Is actually a Lie algebra over the integers. And by inheriting the bracket from L. If we have the field of P elements written like that, which we know is Z over PZ as a field, then we're doing a change of base here in Humphreys. Everyone, I guess, does a change of base eventually. It is a useful tool. An L of our finite field is just our integer span with an integer change of base to our finite field. This is defined. Here that L of the finite field over P is a vector space over our FP with a basis, is taking the chevalley basis, of course, and tensoring 1 on the right. And of course the bracket in our integer span of L induces a natural Lie algebra structure on L of the field, finite field of P. And we know, of course, the multiplication table is just going to be mod P in this case. Don't want to open up Visual Studio Code here. Now, if K is a field extension, any, they specify any field extension of our FP, then LK is, we can either take it from extending our finite field extension of, I guess changing of our finite change of base would be the better term, of L, or just do it directly from the integers. And this inherits inherits is not two words. This inherits a basis and Lie algebra structure from L of the finite field over P of P. And thus we associate with a pair K with a Lie algebra over K, K with a structure resembling that of L. We call L of K, extension of L to K, a chevalley algebra. Now, and says even though the structure of LZ ostensibly depends on the choice of root vectors, it is defined up to isomorphism by over Z by L alone. With similarly LK depending only on the pair of our algebra and the finite field we're extending it to. So, for an example, we're going to let L be SL of rank L plus 1 for some reason over F. Then the chevalley algebra of L over K has the same multiplication as special linear L plus 1 over our F directly. I mean over K directly, we already have it over F. We also do the standard basis, of course. So we have that L of K is isomorphic to SL of L plus 1 of K. The only real change is that LK may not be simple. May not be simple. Having a 1D center of scalar matrices when the character of K divides L plus 1. Essentially, it's saying that the trace of the identity matrix is, of course, equal to its dimension, and so if you're in, say, characteristic 5, then the 5-dimensional identity matrix will have a trace of 5, which is 0, so it will be in the special linear Lie algebra, despite being obviously also going to be in its center, so that will mess things up. Up next, we have construction of chevalley groups. And it's specified here adjoint type. And we start things off here with a proposition. Let alpha be in our root system, m be a positive integer. And then the adjoint of x alpha to the m over m factorial leaves LZ invariant. And so this is obviously going to be setting up our exponential function. Let's get our proof. And so we can of course show that every element of the chevalley basis is sent back into LZ. So we have the adjoint of x alpha on our, say, hi from the chevalley basis. This is definitionally just x alpha bracketed with hi, which is negative of the bracket of alpha with alpha I on x alpha, which is in LZ. While then, of course, higher powers of the x alpha are then going to be by recursion are going to be acting on x alpha itself. So this is going to vanish for m being at least 2. That's supposed to be our factorial. Now, similarly, the adjoint of x alpha on x negative alpha is just h alpha in L of the integer spans. Now, the adjoint of x alpha squared over 2 on x negative alpha is going to be 1/2 of the bracket of x alpha on h alpha is negative x alpha in LZ, and higher powers disappear as before. Yeah. And so of course all adjoints of x alpha to the m over m factorial on x alpha are going to be 0. So we need it for x beta, with beta not being plus or minus alpha, of course. If the alpha string through beta is beta minus r alpha through beta plus q alpha, then the integers which play the role of r for beta plus alpha up to beta plus q alpha are 1 plus 1 through r plus q. Thus, the adjoint of x alpha to the m over m factorial on x beta is going to be plus or minus r plus 1 multiplied through r plus m over m factorial times x beta plus m alpha. or it's going to be 0 if beta plus m alpha is not a root. The coefficient is just r plus m, choose m. So the right hand side is an integral multiple of x beta plus m alpha. And this is, of course, going to be setting up our exponential action, as I said. So, to talk about why this is important, L is a module for the adjoint representation of L, and L of Z is a lattice in L, stable under the endomorphisms adjoint x alpha to the m over m factorial hence under the exponential of the adjoint of x alpha. And we saw that this is nilpotent. Every basis action we saw terminated eventually, so this is going to expand out to an infinite sum. Relative to the chevalley basis, the interior automorphisms of L as G can be thought of as a group of matrices and the subgroup generated by all of the exponentials of the adjoints of Cx alpha for alpha in our root system and C being an arbitrary integer leaves Lz invariant. Hence consists of matrices with integral coefficients. Undeterminate 1. So, in particular, if P is a prime with sorry about that. That's with associated finite field Fp, then reducing all matrices mod P yields a matrix group over Fp, which acts on the Lie algebra L of Fp, our chevalley algebra over Fp of L, as a group of automorphisms, which we denote as G of FP. I really messed up that field F, the blackboard F. We can generalize this, I think, a bit here. So we're going to let T be an indeterminate. Then the matrix group generated by all exponentials of the adjoints of Tx alpha, for alpha being a root, of course, consists of matrices with coefficients in ZT, and both in this case and in a previous case they have determinant 1. So that's specializing T2 elements of an arbitrary extension field K of FP yields a matrix group GK over K, which is called a chevalley group of adjoint type. When K is finite, this group is finite and usually simple. It says there's some exceptions, but it's worded, I think it's probably like a finite number of non-simple chevalley groups. And you can make some like new, otherwise unknown groups in this way. Alright, we'll move on to our next section. I keep kind of alternating between section and chapter too freely, and it makes it hard to know exactly where we are in the book. But this is on Constant's theorem. So we're gonna, and for this, our setup, we fix a semi-simple Lie algebra with Cartan subalgebra H, and root system phi with base delta, and a chevalley basis x alpha and hi. Now, so to construct matrix groups associated with arbitrary representations, say phi of L, we must work inside the universal enveloping algebra of L. We aim to construct a lattice analogous to LZ in an arbitrary finite dimensional, of course, L module, invariant under all endomorphisms, which is kind of phi x alpha to the m over m factorial, so it's actually kind of generalizing what we just did with chevalley groups. Now this construction will utilize and what they call an integer form in scare quotes of the universal enveloping algebra of L, which is going to turn out to be the subring with 1 of the universal enveloping algebra of L generated by all x alpha to the m over m factorial. This brings us to our first subsection, which is just, I think, working through a single lemma. Setting up and then working through a single lemma, yeah. And so it's just called a combinatorial lemma. If we replace n in n choose k, which is recall as the product of n through n minus k plus 1 over k factorial. It's an element x of a commutative associative F algebra. The resulting expression still makes sense. And can be denoted in the way that you would expect as x choose k, for k being a positive integer. We also have the familiar identity of n plus 1 choose k minus n choose k being n of k minus choose k minus 1. And this is going to carry over. And as usual, n choose k is 0 if k is negative, and n choose 0 is going to be 1. Brings us to our lemma. We can have L determinants and T. With F being f of t1 through tl, a polynomial over our field such that f of n1 through nl is an integer when n1 through nl are integers. Then f is an integer linear combination of our ti choose bi, for I of course being 1 to l. This double parentheses is the inner one, is our choice operator, and the outer one is showing that we have a sequence from 1 through l, where b1 through bl are positive integers, and hbi does not exceed the degree of f as a polynomial in the respective ti. Our proof. First, we note that ti choose bi, which is ti minus 1, of course, through ti minus bi plus 1 over bi is an integer when ti is replaced by an integer. Kind of abusive notation there, but don't worry about that. And we also notice that these polynomials form an f basis for the polynomial ring of t1 through tl, and we prove by induction on L and the degree of f in TL. ff is a constant polynomial. It is an integral multiple of 1, which is TL choose 0, and so we're done. That's our base case. In general, we can write f as the sum from k being 0 to r of fk of t1 through, I should write this better, t1 through tl minus 1 times tl choose k, where r is the degree of f in TL, fk of t1 through tl minus 1 is in the field of f, field of t1 over t1 through tl minus 1. Next, we can formally substitute TL plus 1 for TL on both sides and subtract. And we get then the right hand side is going to be the sum from 0 to r of fk t1 through tl minus 1 times tl, choose k minus 1, while the left hand side is a polynomial satisfying the original hypothesis. Now, we can repeat this. Repeat this process r times until the only non-zero coefficient on the right hand side is TL, choose r minus r, which is going to be 0, so that's going to be 1. And this is going to be the coefficient of fr of t1 through tl minus 1. Now fr satisfies the hypothesis, but has one fewer variable than f. By induction, fr can be expressed in the desired fashion. And f minus fr t1 through tl minus 1 times tl, choose r, satisfies the hypothesis. You can tell my hand is tired by how messy the ratings get. And is of degree less than r in TL. So induction completes. And so we're going to be looking at this next time. Specifically on SL2, we're going to look at how commutation works a bit better. And we might end up proving this thing. It doesn't appear to be too long of a section in our chapter here. So look forward to that next time, I guess. Thanks for watching.